Find the following indefinite integrals. So we've got the integral of ln of 2x plus 3 dx and the integral of arc sine 2x dx. Now both of these are done by parts, surprisingly. So for ln of 2x plus 3 dx, we need to think of it as 1 times ln of 2x plus 3 dx. So using integration by parts, if we let u be equal to ln of 2x plus 3, now that seems a bit surprising, but you can't actually integrate it directly because that's what we're trying to do. So we have to let that be u because we know we can differentiate that. That's just going to be 2 over 2x plus 3. And dv by dx will be the 1. If we integrate 1, we're going to get 1 integral 1 dx, which is x. And then the integral of parts by parts is u dv by dx is equal to uv minus the integral of v du by dx. So the integral of ln of 2x plus 3 dx is going to be u v, which is x. So we're going to write it as vx. So we're going to write it straight away as x times ln of 2x plus 3 minus it 2. The 2 is going to come from this 2 here, and the v is x, so this is going to be 2x over 2x plus 3. I've just taken the 2 out. Right, this is actually an improper algebraic fraction, so before we can actually integrate it, we must do a division first. So doing 2x plus 3 into x gives a half. A half times 2x gives x, a half times 3 gives 3 over 2, so we get a remainder of minus 3 over 2. When we do 0, take away 3 over 2. So my integral can now be written as 1 minus 3 over 2x plus 3 over 2, because I've got 3 over 2, 1 half minus 3 over 2 when I rewrite it once I've done the division, so that 2 can come out. The 2's will cancel, which is quite nice. And then I get the x ln of 2x minus 3. If I integrate 1, I'm just going to get x. And then if I integrate this, I just get 3 ln of 2x plus 3. But I need to change the sign for a plus because a minus times a minus is a plus. And I also will need a extra 2 because when I differentiate that back, I'm going to get a 2 extra 2 over 2x plus 3. I don't want 2, so I need to put that half in there. You can write the differentiation out for yourself to check that that's true. And that gives me the final answer. For the second one, again, you need to write arctan in the form as 1 times arctan of 2x dx. So if you let u be equal to arctan 2x, because that's what we're actually trying to integrate, so we'll differentiate it, because we can differentiate it. It's a standard integral, so it's 1 over 1, standard differentiation, 1 over 1 plus 2x squared. And because the 2 there, then we have to put an extra 2 at the top. All right, in fact, it gives you a 4, so that's why you need the extra 2 at the top. So that gives me 2 over 1 plus 4x. If you're not sure, just stop the video here and sort of try and practice differentiating this for yourselves. So dv by dx is 1, and like we got before, we got that v will be x if we do that. Using integration by parts, we're going to get uv. So we're going to write v u, which is x arctan of 2x, minus the integral of, combining these two here, 2x over 1 plus 4x squared. We'll call that equation 1, and then we will write it out again so we can get it clear. Now, if we want to look at this integral here, we will have to let we do it by substitution. So let u be equal to 1 plus 4x squared. If we differentiate that, we're going to get 8x, nothing from the 1, and then 2 times 4, which gives 8x. And therefore dx is du over 8x. So that's good because the x's will cancel. And then the 8 and the 2 will cancel to give a quarter. So we have a quarter of the integral of 1 over u du and that gives me 1/4 ln of u plus c, but u was my invention, so I'll put it back, so get 1/4 of ln of 1 plus 4x squared plus c. And then if we substitute that back into equation 1, we're going to get our final answer. The integral of arctan 2x is arctan 2x minus 1/4 ln of the absolute value of 1 plus 4x squared. Except we don't actually need the two straight lines, because 1 plus 4x squared can never actually be negative. Take out those two straight lines and put the curved lines in instead, plus c. Okay, so this has been a video to show you how to do special integrations using integration by parts. I hope you've understood, and I thank you very much for watching.